Section 2A, the problem-solving power of units. So kind of an interesting name for the section. I would probably change this to unit conversion as the main topic that we're going to cover, and then we'll also be looking at a little bit with some geometry. So let's go ahead and start off with the unit conversion. So we're going to use conversion factors to convert each of the following, starting off with part A, converting 24 feet to yards. So the way we're going to approach this is we're going to take the amount that they started us off with, which is the 24 feet, and we're going to write that over 1 so that it looks like a fraction. And then we want to multiply that by what's called a conversion factor, and the job of the conversion factor is to switch the units from the units we have to the units we want. And the units we have are feet, and the units we want are yards. So the way we're going to do this is multiply by a new fraction where our main goal is to have units cancel out that we want to get rid of and then have them replaced by the new ones. So I want to get rid of feet, and feet are in the numerator right now, so I'm going to put feet in the denominator of this conversion factor, and that will cause the feet to cancel out. And I want to replace feet with yards, so that unit I want to take over I'm going to put in the numerator. And then to make this process work, what I have to do is fill in numbers here so that the top and bottom are equal. That way I'm multiplying by a fraction where the numerator and denominator are equal. That means the fraction has a value of 1, and it's not going to change the value of my original quantity, though it will convert the units. So the conversion that I need to know is that 3 feet equals 1 yard. I'll go ahead and write that off to the side over here. But 3 feet and 1 yard are the same amount of distance, so when I fill those in I have the same amount on top and bottom, so essentially I'm multiplying by 1, but in a way that cancels off the units I'm trying to get rid of and replaces them by the units that I want. And then as I go through to finish this off, I just do the math on this. Numbers that are in the denominator are numbers that we're dividing by. I normally wouldn't do this, but I'm going to go ahead and multiply across, so I'd have 24 times 1, which is 24 yards, over 1 times 3, which would be 3, and no units on the bottom because the feet canceled. And then this 3 goes into that 24 8 times, so I'm left with an answer of 8 yards. So apparently 24 feet is the same measure as 8 yards. And I said I wouldn't normally do this step. I normally would just do 24 divided by 3 equals 8 and just kind of skip right over that to the answer. But if you want to multiply across and then do your cancellation afterwards, you can do that. It's just a little bit more of a cautious approach. Alright, let's go ahead and take a look at another one, part B. Convert 2.5 hours to seconds. So same approach. I'm going to start off by taking the amount they gave me, 2.5 hours, and write that as a fraction by placing it over 1. And then I'm going to start thinking about trying to get rid of the units that I have and move towards the units I want by using a conversion factor. So I'm going to put hours on the bottom here so that the hours will cancel out. And what would be awesome is if I could put seconds up in the top, because then I'd go from the units that I have, hours, straight to the units I want, which is seconds. But the problem is I don't know how many seconds there are in an hour off the top of my head. So what I'm going to do instead is put an answer that's in between hours and seconds that I do know the answer for, which is minutes. And I know that there is 60 minutes in 1 hour, so I'm going to fill those in so that the top and bottom are both equal amounts of time, 60 minutes in 1 hour. And the cancellation there of hours would switch this to minutes. But I don't want minutes, I want seconds. So what I do in that case is I bring in a new conversion factor and say, alright, let's get rid of the minutes now and switch over to what we really want, which is seconds. And the key question that people will want to know on these things is, how do you know what goes in the top versus the bottom? Where there's seconds or minutes, where do they go? And the answer is you're trying to make these minutes cancel. So if the minutes are in the numerator on this fraction, they need to be in the denominator on this other one, so that when I multiply they'll cancel. And then where do the numbers go? Well, that's just a matter of making sure that things are equal. So 60 seconds equals 1 minute, so I have to write those just like I would say it. 60 seconds is 1 minute, and that way top and bottom are the same amount of time. And if you look at what happens here, the hours cancel, the minutes cancel, and then I'm left with just seconds as the units, which is what they wanted me to do. And when everything is in the numerator, we just multiply across. There'd be a 1 in the denominator, but we can just ignore that because anything over 1 is itself. So my answer is just whatever I get by doing 2.5 times 60 times 60. So I'm just going to bring in the calculator real quick and do that computation. So 2.5 times 60 times 60 is 9,000. So it's going to be 9,000 seconds for 2.5 hours. Oops, missed my C there. Throw that in. Alright, let's continue on. Look at a couple more of these. So let's go ahead and convert 3.75 acres to units of square feet. And this is one that off the top of my head I wouldn't have known. I do know that an acre is roughly 40,000 square feet, but I didn't have it memorized that it was 43,560 square feet. It's common that if it's a messy conversion like this that it'll be provided. But the math is still the same. I want to start off by taking the 3.75 acres that they gave me and write that as a fraction by putting it over 1. And then I want to think about making the acres go away. So since the acres are in the numerator in the original, I want acres in the denominator of my conversion factor, and I want to replace that with what it's equal to, which is square feet in the numerator, which is also my target. And then where's the 45,060 go? Well, it's with square feet right here, so it still goes with the square feet in the conversion factor, and then it was 1 acre, so I put 1 acre down there. And then the acres would cancel. The new units would be square feet. When the number in the conversion factor is in the numerator, it's a number that you would multiply, so I'm just going to multiply straight across. And bring in the calculator real quick for that. 3.75 times 43,560, and it looks like 163,350. And then there's the question of units. Well, we can just look at what we've got written here. The acres have canceled off, the square feet remain, so it's 163,350 square feet. Alright, let's go ahead and look at the final one, part D. They want us to convert 1 ton, which is 2,000 pounds, to ounces. So you could take this to be 1 ton equals 2,000 pounds. So I'm just going to go ahead and start off by writing the 1 ton. And I'll put that over 1. And then I want to convert that to pounds. And they're basically just telling me it's 2,000 pounds, but I'll show you it as a conversion. So the first thing when I do conversion factors, I always put the units before the numbers because it's the units that I'm thinking about in terms of what goes top and bottom. I have tons on the numerator here, so I want tons in the denominator here so that they will cancel out. And then I'm going to convert that to pounds at first, which is the abbreviation is LBS for that. And then what are they telling me here? 2,000 pounds equals 1 ton, so 2,000 pounds is 1 ton, and at this point I'll be able to cancel those initial units of tons off and be converted over to pounds, but pounds isn't the goal. Ounces is the goal, so I need another conversion factor. And right now I have units of pounds, and I'm trying to get rid of those, so I'll put pounds in the denominator because the other pounds are in the numerator, that way they'll cancel off. And then I can put my ounces up top. And then I just need to know how many ounces there are in a pound. And before I fill that in though, just another reminder, units come first. Don't try and put the numbers first, put the units first. If pounds are in the numerator, put pounds in the denominator so that they will cancel off. And then figure out where the numbers go, just make sure they match up with the units. So this one you may or may not know off the top of your head, but 16 ounces is equal to 1 pound. And so I'm just going to fill that in. 16 ounces is 1 pound. The numbers go with the same units here that they do in the equality over here. And I have all numbers in the numerator again, so there's no division to do. So I just need to multiply across. The tons have canceled, the pounds have canceled. My answer is going to be ounces now. It's just a question of how many ounces is that. So I bring in the calculator and I have that 2,000 times the 16 is 32,000. And again on the units, the tons have canceled, the pounds have canceled, so it's ounces. Alright, so in all of these problems that we just did, the key thing was to use a conversion factor to switch from the units we started with either closer to the units we wanted or directly to the units we wanted. And a conversion factor is a fraction where the numerator and denominator have different units, but they still represent the same quantity. So for example, 2,000 pounds and 1 ton, those are different units, but they represent the same amount of weight. 16 ounces and 1 pound, those are different units, but they represent the same amount of weight. And we're always trying to use these conversion factors to help us do our conversions, especially more complicated ones where we have to move through multiple stages. Alright, moving on to page 2 of section 2A, we're going to go ahead and look at some basic geometry calculations of area and volume. And we're going to have some units along the way and just talk about how showing the units through those calculations can help us know if we have a right answer. So a warehouse is 40 yards long and 25 yards wide, and it's piled with cartons to a height of 3 yards. What's the area of the warehouse floor, and what is the total volume of the cartons? So first we'll do the area of the warehouse floor, and they didn't say this, but when they say that it's so many yards long and so many yards wide, it sounds like it's a rectangle. So I'm going to use the area equals length times width formula for a rectangle. And I'm going to show the units as I do the calculation like they requested. So it says it's 40 yards long, so I'm going to put 40 and yards. And then I'm going to multiply that by the width, which is 25 yards. And we can do the math on the numbers. 40 times 25, I believe, is 1,000. Yep, just verified that on the calculator. So we have 1,000. And then the other thing that they want us to see is that if we have yards times yards, then just like x times x would be x squared, yards times yards would be yards squared. So that's 1,000 square yards for the area. And when you do area, you should expect to get square units. So typically square feet, square yards, square miles, something like that. So if you show your units and it comes out square yards and you know you were doing an area, that's a good sign. So it's kind of a check to have those units carried along to make sure you didn't miss something. And then what's the total volume of the carton? Anytime you have an area of a three-dimensional object and then you add in knowing how tall that object is, as long as it's going straight up, then the volume becomes that area times the height. So the volume will become the area of the base, we would say, times the height. And in this case, we already know the area of the base formula is length times width, and then we'd also have the height, so we'll put an h there. And I'm going to go ahead and show the whole calculation, even though we do already know the area. So the area of the base would be 40 yards times 25 yards, and then the height would be, let's see, it was given as a height of 3 yards that the cartons were stacked to. So now when we multiply this through, we have the 40 times 25 is 1,000 times another 3 will take us to 3,000, but then what are the units? Well, this time we don't have yards times yards, we have yards times yards times yards. So instead of square yards, we're going to get yards to the third, or people would often say cubic yards. So 3,000 cubic yards is the volume of these cartons. Alright, let's try that on another one. So moving on to part B, the bed of a truck is 3.5 feet deep, 12 feet long, and 5 feet wide. What's the area of the floor? What's the volume of the bed? So this is actually the same situation again. Area would be length times width, and it says that the length is 12 feet and the width is 5 feet. So we multiply the 12 times 5 and we get 60, and the feet times feet and we get square feet, so 60 square feet. And then when we do the volume, it's length times width times height, so it's still that same 12 feet times 5 feet, and now times the height, which could also be considered this depth, would be another way of writing that, so times 3.5 feet deep. And I think I could use this times the 3.5. I'm just going to go ahead and go to the calculator on this. So numerically, I have 12 times 5 times 3.5, so that's 210. And then when I look at the units, I have feet times feet times feet, so that would be feet to the third or cubic feet. So the area is 60 square feet and the volume is 210 cubic feet. And so you expect anytime you do an area you should get square feet, and anytime, well, square units, and anytime you do a volume you expect to get cubic units. There's some exceptions to that, but that's kind of the standard thing. So carrying the units along and seeing that work out as expected is just kind of a good mental check on that things are going well. And then let's look at one final one. A can has a circular base with an area of 6 square inches and it's 4 inches tall, so what's its total volume? So they're just going straight to volume this time, and as I said up above, on anything that has a known base and then goes straight up, the volume would be the area of the base times the height. So in this case the area of the base is provided, it's 6 square inches, and notice that that actually makes sense because it's an area, so for it to have units that are inches squared fits that pattern. And then the height is given as 4 inches tall, so you'd multiply the numbers, 6 times 4, and you'd get 24, and then you'd take the units and multiply those. Inches squared times inches to the first would be inches to the third, and cubic inches is what you should expect from a volume, and that is what we get. And so when the units work out, that's just a good signal that things are going well. Okay, so we're continuing on with section 2A on doing conversions. Let's go ahead and look at an example. Find the area in square feet of a rectangular yard that measures 20 yards by 12 yards. So the first thing to notice is they want us to find the area, and in all the problems we've been doing so far, we've started out with the number they wanted us to convert. This time we don't know the area, we know the dimensions of this are 20 by 12. So I'd start off trying to find that area. So I'd write down the area formula. It is a rectangular yard, so area is equal to length times width. And I would plug in the numbers that they gave me, which would be 20 yards times 12 yards. And when I do that multiplication, 2 times 12 would be 24, and then we have the zeros, so that would be 240. And then the yards times yards would end up as square yards. So now we have the area in square yards, but they want us to have that in square feet. So we're going to need to take this and convert it. So I'm going to take that 240 square yards, and I'm going to put that over 1, and then I'm going to want to multiply that by a conversion factor like we've been doing on the other problems. And since I'm trying to get rid of the square yards, I would put square yards in the denominator, and I want to have square feet in my answer, so up top in the numerator I would put square feet, and then it's a matter of filling this in. Now we know that there's 3 feet in a yard, but we don't necessarily know how many square feet there are in a square yard. And one way you can figure that out is to take the conversion factor you know, which in this case would be that there's 3 feet, and that equals 1 yard. And you can, to get the units you want, which are square units, you can square both sides of this, and then you would get 9, and you would square both the number and the units, so 9 square feet equals, well, 1 squared is still 1, and it would be 1 yard squared. So from the conversion we knew 3 feet was equal to 1 yard. We can square both sides and get that 9 square feet equals 1 square yard. And once we have that, we can fill that in. So it would be the 9 up here with the square feet, and the 1 down here for the square yards. And at this point we could say the yards squared cancel out, just like we've been doing in previous problems. The 9 is in the numerator, so that would be multiplied with the 240. And 9 times 240 is 2160. So that would be our number, and then the new units that are left over are the square feet. So we found the area is 240 square yards, and then we converted that to square feet, and we got our new conversion factor by taking the one we already knew and squaring that. And again, we have kind of work all over the place, so I would box this to make sure my answer is really clear. And then the note that I'd want to make on this is what we did over here on the side, because that was new. So if you're trying to convert areas, then you must square the numbers that are in the standard conversion factor that you know, And again, I think the best way to do that is as scratch work over on the side where you write the conversion factor down, and then since you want square units, you square both sides. Let's look at something really similar to that with volume and see another example. So a hot tub pump circulates 4 cubic feet of water per minute. How many cubic inches of water does it circulate each minute? So we're going to try and make a conversion of 4 cubic feet of water per minute. So the first thing I'm going to do is write that down. 4 cubic feet I'll write as 4 feet cubed, and then it says per minute, so I'm going to put that as over a minute, and then I'm going to try and convert that, and when I'm done I want it to be, let's see, cubic inches and each minute or still per minute. So the minutes aren't going to change, but I want to get rid of these cubic feet and convert that over to cubic inches. So I would multiply by a conversion factor where I put feet cubed on the bottom because that's what I'm trying to get rid of, and then we want to end up with cubic inches, so I'll put inches cubed on the top. And then we're in a really similar situation to the last one. We do know there's 12 inches in a foot, but we don't know how many cubic inches there are in a cubic foot. So we just use the same trick that we did before. We go over here to the side and we say there's 12 inches and that's equal to 1 foot. And then since we want cubic units here, then instead of squaring like we did last time, we'll cube both sides or raise each side to the third power. And so 12 to the third, I'll do that on the calculator off to the side, is 1728. And that's what I get from raising 12 to the third power, and I would also take the inches and raise that to the third power. And if you take 1 to any power, it stays 1, and then the feet to the third would become feet cubed. So it looks like there's 1728 cubic inches in 1 cubic foot. So I can say 1 cubic foot down here and 1728 cubic inches in the numerator. The units of the feet cubed would cancel off. I would have inches cubed in the numerator and minutes in the bottom, and I could read that as inches cubed per minute or inches cubed each minute, same idea. So it looks like we've got the units worked out, so now we just want to work with the numbers. And we have our multiplier here because it's in the numerator. So I'm going to do 4 times 1728, and I get 6912. And then the units on that would be inches cubed, and I could say per minute. So it looks like how many cubic inches of water does it circulate per minute? 6,912 cubic inches every minute for this hot tub pump. And if you look at what the trick was for this one, to convert a volume, you must cube the numbers in the standard conversion factors. So I took that standard conversion factor that I knew, I cubed both sides, and that gave me the conversion factor that I needed. And again, some work kind of all over the place, so here's my answer, and I'll box that to make it clear. Alright, let's look at another example of conversions. A hose fills a hot tub at a rate of 3.2 gallons per minute. How many hours will it take to fill a 300-gallon hot tub? And then we're going to round our answer to 2 decimal places on this one. So one of the things that I've noticed with people in the past on this is they'll try and take the 3.2 and convert it, but that's not what we're being asked to do. They're asking us how many hours will it take to fill a 300-gallon hot tub. So essentially they're asking us to convert 300 gallons to hours, so that's the conversion we want to make. So I'm going to start off by writing that 300 gallons down. And then I'm going to put that over 1, and this is the conversion that I want to make. And when I'm done, I want the gallons to be gone, and I want hours to take over. And so to do that, that's where the 3.2 comes in. When they tell me that the hose fills the hot tub at a rate of 3.2 gallons per minute, they're actually giving me a conversion factor there that says that 3.2 gallons is equal to 1 minute of time. And I'm going to use that as a conversion factor in this problem. So I'm going to set this up with gallons on the bottom because I'm trying to get rid of those gallons. I'm going to use this conversion factor. So the other units in the problem would be minutes. The 3.2 gallons is 3.2 is with the word gallons, so I'm going to put that down here in the denominator where we have gallons, and then with the minutes we have a 1, so that'll go up here. And if we do the cancellation of units, we see the gallons are going away, and now we'd have this in minutes, but the question said how many hours. So I'm going to multiply by another conversion factor, trying to get rid of the minutes. They're in the numerator now, so I'm going to put minutes in the denominator, and I'm going to put hours in the numerator to kind of take over after those cancel off. And this is a conversion factor that we know already. There's 60 minutes in 1 hour. So now I can cancel off those minutes, and I have the only units that are left are hours. So this is all set up right. Now I just need to do the math on it. Numbers that are in the denominator of your conversion factor are numbers that you want to divide by. And since there's 2 conversion factors here and it's getting a little messier, I'll go ahead and show you that, and I'll show you it 2 different ways on the calculator. Let me slide this over a little bit so we can see the calculator. And I'll clear out some old stuff here. So I have 300, and then I could just multiply by this fraction times 1 over 3.2, and then I could multiply by the next fraction in our next conversion factor, so times 1 over 60. And that should get me to the number that I need, so it looks like 1.5625. So that's one way to do it. Another possibility is a little faster, and you can pick which one you like better, is to start with the 300, and when you look at a conversion factor, if the number that's not a 1 is in the top, multiply by it, but if it's in the denominator, divide by it. So I could just go divided by 3.2, and I could go to the next fraction and just think the same way. Where's the number that's not a 1? The 60 is in the denominator. Since it's in the denominator, I'll divide by it. And you can see that on the calculator, either way I do that, I get the same answer. So whichever one feels smoother to you, makes more sense to you, they both work, so you can pick which one you would like to do. So let's go ahead and write our answer on that one. So it was a little bit messy on the decimal, and they asked us to round it to 2 decimal places. So since I'm rounding, I'm going to put the approximately equal symbol. And on the calculator, I had 1.56, and it was a 2.5. But they said to 2 decimal places, so I'm going to stop at the 6, and the decimal after that was a 2. So I'll just stop there. And as far as units go, the gallons are gone, the minutes are gone, but the hours are still there. So 1.56 hours would be my answer. And we'll go ahead and circle that. Alright, now we're going to move on to doing conversions for money. And if you want to do conversions involving different kinds of money, then you need conversion factors for that. So the tricky thing about this is the conversion factors for money change every day, unlike things like there's 12 inches in a foot, which is there kind of forever for us. The money exchange rates are always fluctuating. So the currency exchange rates I have here are from February of 2013, and even at the time I'm making this video, these are kind of old, but they're the ones that the book uses. So I'm going to show you with these conversion factors so that you can use this same chart when you're doing homework in my math lab and have a convenient chart for that. I think the way they list the chart in the book for money is kind of confusing. So this is a nice what equals what sort of chart, and I'll show you how to use it in this example. So as you leave Paris, you convert 4,500 euros to dollars. So how many dollars do you receive? And round to the nearest penny or to the nearest cent. Alright, so these work like normal conversions. You start out by writing what you were given, 4,500 euro. Euro kind of is like an E with 2 lines in a way. That's probably not a great version of it, but it looks something like that. You can just write out the word euro if you want. And then we'll put it over 1. And then when we do conversions, we always want to think about what units are we trying to get rid of, euro, and put that in the bottom, so that the euros on the bottom and euros on the top will cancel. And what are we trying to convert to? It says to dollars, so I'll put dollars on the top. And then we need to know how many dollars per euro. So for the euro, everything here is going to be connected to the dollar for us. There's 1.320 dollars in 1 euro, so I could put 1.320 on top and a 1 on the bottom. Or there's $1, and I could put a 1 up top, is 0.7576 euro. You can do either one of those. I personally like to always pick the one that makes the denominator a 1 when I have a choice, so I'm going to go with 1 euro. and €1 equals $1.320. And then the euros cancel, and both my numbers are in the numerator, so I'll just multiply. It's going to come out kind of messy, and they want me to round to the nearest penny, which is 2 decimal places, so I'll do that. Let's bring in the calculator, and we have that 4,500 times 1.320 is 5940. Okay, so much for the approximate equals. I should have thought about that. Because I'm not dividing, I get nicer answers. So $5,940 is the same as 4,500 euros. So we ended up not having to do that. I guess I should put 0.00 because then I am going to the nearest penny just to match with what they said. Now that rounding would have mattered if I did it the other way, so I want to go ahead and point that out to you. Another option, let's do it in another color here. I could have started with the 4,500 euro and then set up the units in the same way. Euros on the bottom so they'll cancel, dollars up top. But then I could have used this conversion factor, that $1 is equal to 0.7576 euro. Now if I do that, the euros still cancel, but when I go to the calculator, it's 4,500 times 1 over 0.7576. And because it's a division, it comes out messy, so then I would need to round it to 2 decimal places, which would be 5939.80, but the 9 would make me round up there, so that would be 81. So notice I get something slightly different, and we'll learn about this a little bit more in the next chapter. But when you have these conversion factors, they did some rounding. So they rounded it to 4 digits here, 1, 2, 3, 4, and this one is rounded 1, 2, 3, 4. And when you round something to 4 digits, it's hard to trust 6 digits later on. In fact, you probably can't. So the truth is probably somewhere in between these two answers, but they're really similar to each other. In fact, if you rounded them to 4 decimal places, this one was already 5940, but this would become 5940 also, because that 8 would cause the 39 to round up. So you will get slightly different answers. I believe my math lab is programmed to take either one of those because they're prepared for you to use either conversion factor. Okay, we're moving on to the last page of section 2A on conversions, and we're just going to look at kind of an interesting problem here that deals with how changing your speed when you're driving affects, of course, how long it takes you to get to your destination, but also how much gas you use and therefore how much money you spend. So suppose your car averages 25 miles per gallon on the highway if your average speed is 60 miles per hour, and it averages 25 miles per hour on the highway if your average speed is 75 miles per hour. So these numbers can vary a little bit from car to car, but it generally is true that if you go at a slower rate of speed, you're going to get better gas mileage. So what is the driving time for a 1,500 mile trip if you drive at an average speed of 60 miles per hour, and what is the driving time at 60 miles per hour? So we're going to do both of those scenarios and make a comparison. So we'll start off with the 60 miles per hour situation. And the way I'm going to treat this is as a conversion. They're saying what's the driving time for a 1,500 mile trip? So I'm going to try and convert 1,500 miles to time. So I'm going to start out by writing 1,500 miles, and I'm going to put that over 1, and I'm going to try and convert that to time. So if I'm going to do that, I'm going to try and get rid of the units of miles, and I need a conversion factor that goes from miles to time to do that, and we're going to use our speed as that conversion factor. It says 60 miles per hour, which we would think of that as 60 miles over an hour, but you could also think of it as a conversion factor and say in this situation 60 miles equals 1 hour. So I'm going to put hours on the top, and again if I read that as an equals for the per, 60 miles equals an hour. So 60 miles equals 1 hour. So I'll write that 60 down there in the denominator with the miles. Then I can cancel the miles off, and because the 60 is in the denominator, I'll do a division, and that should give me the number of hours. So 1,500 divided by 60 is 25, And the units would be the units that are left over, which would be hours. So it looks like if you were to take this rather long trip about halfway across the US at 60 miles per hour, it would take you about 25 hours of drive time to do that. So what if you pushed down a little harder on that gas pedal and went 75 miles per hour? Then what would it be? So 1,500 miles over 1, and we're going to do that same scenario, that same kind of methodology that says we're going to treat this speed, 75 miles per hour, as a conversion factor. I'll put miles on the bottom because I want the miles to cancel, and so the hours will go on top. And then I'm going to read this as 75 miles equals 1 hour. So 75 miles equals, your fraction bar, 1 hour. The miles cancel again. Our 75 is in the denominator, so we'll divide by that. And 1,500 divided by 75 gives us 20. So it should take 20 hours to do that drive if you were going faster at 75 miles per hour. And they didn't ask this, but worth just a quick note. By going faster, we saved 5 hours. But was there a cost for that savings? And so we're going to look at that in the second part. So assume a gasoline price of about $3.75 per gallon. What is the gasoline cost for that 1,500 mile trip if you drive at an average of 60 miles per hour? And what is the gasoline cost if you drive at 75 miles per hour? So again, they're asking us two questions. So we'll look at it for 60, and then when we're done with that, we'll look at it again for 75. So this 3.75 per gallon is not what we want to convert. That's a conversion factor. What we're trying to convert is 1,500 miles to a cost. So I'm going to start again like I did before with 1,500 miles and then put that over 1. And this time my goal, instead of converting that to a time, is to convert that to a number of dollars that I'm going to spend on gas. So we got to look up top here, and it says if we're doing 60 miles an hour, if we're doing 60 miles an hour, then we're getting 25 miles per gallon. Well, we're going to use that as a conversion factor, that 25 miles is equal to 1 gallon. So down here, I want the miles to cancel, so I'm going to put those in the denominator. And then that means if I'm putting miles in the denominator, I'll put the gallons up in the numerator. And then using this as a conversion factor, I apologize, it is 32 miles per gallon. Caught that just in time. It's 32 miles per gallon on the highway if we're doing 60. So it's going to be 32 miles is equal to 1 gallon of gas. And we can cancel off the miles there, and now we'd have this converted to gallons if we did the math. But we're not trying to figure out gallons, we're trying to figure out the cost. And that's where this comes in. The price is $3.75 per gallon. So I want to get rid of these gallons, end up with money, and I'm going to use this as my conversion factor. It's $3.75 per, or equal to, each 1 gallon. And so this is going to be my conversion chain. The gallons are going to cancel off now. I'm going to have the dollars that I want, and I just need to do the math on that. So the way I would do this, and I'll go ahead and show it to you on the calculator. Let me slide this over a bit. I would take the initial 1,500 that we're starting with. Let's clear out those old numbers. So 1,500, and the 32 is in the denominator, so I would divide by 32, and then the 3.75 is in the numerator, so times 3.75. And when I multiply that all out, I get approximately $175.78 if I were to round that to the nearest penny on how much the gas would cost. Now, it actually didn't give me any rounding directions, but that would be pretty standard for something involving money to round to the nearest penny. So there's our cost if we do the slower speed. What if we want to save those 5 hours by going 75 miles per hour instead? It's almost the same math. We have the 1,500 miles. We put that over 1. We're going to cancel out the miles and replace that by gallons. But if we go back up to the top at the problem, it says this is where that other number comes in. If we're doing 75 miles per hour, now it's 25 miles per gallon. So 25 miles equals 1 gallon if this is our speed. So 25 miles is equal to 1 gallon. And again, that's coming from this opening paragraph that says if we're doing 75, our fuel efficiency is 25 miles per gallon, or 25 miles equals 1 gallon. So I filled that in, and that's going to allow the miles to cancel. But just like last time, I still need to get rid of the gallons and convert that over to dollars. And I use the exact same conversion factor that gas costs $3.75 per 1 gallon. They don't charge us more money just because we're going faster. We'll use more gas, but they still charge the same amount. And we'll do the same math on the calculator, just with one substitution. We'll be putting the 25 instead of the 32. This time I'm going to show that to you using the other way of entering it, just so you can see both options. So 1500 times, I'm going to just do the whole fraction this time, 1 over 25, and then times 3.75 over 1, and I get 225. And you can see there, if you were to ignore the pennies, it looks like we're spending about $50 extra there. But we'll get at that exactly in the next part. So let's go ahead and take a look at the final piece. How much are you paying per hour for the time that you save? So how much are you paying per hour? So paying, cost, per hour, so over hours. So how much time did we save? Well, we already kind of looked at that up in part A. We had 25 hours dropping down to 20 hours, so we were saving 5 hours. And how much money did we save? Or actually, how much money did it cost us, really? And so I'm just going to do that difference here and say it's 225 minus 175.78. And I'm going to go ahead and just put all that into the calculator at once. And we'll need those parentheses because we have more than one number in the numerator. And let's see what we get for that. So parentheses, and 225 minus 175.78, which is about $50. 50 divided by 5 should be about $10 per hour, I think. But let's go ahead and do it with the decimals in there. And I thought it'd be about $10 per hour. I'm getting 9.84, so that's just because of the pennies. It's changing that a little bit, so that sounds right. And you could write the whole thing, but again, it's money. I would probably convert it to the nearest penny, or round it to the nearest penny, and so I would use 2 decimal places there. So I'm going to put that that's approximately $9.84 per hour. So that's how much we're spending per hour saved. So is it worth it? Right? That's something that we'd have to decide, I guess. Is it worth that money? One of the things that students often point out in class about this is, in addition to the extra $10 an hour, we're also at 75 miles an hour on some freeways risking a speeding ticket, and then there's an extra cost associated with that. But we'll leave that out of these calculations.